which is just essentially effectively just English prose, describing the step-by-step stages and so forth. Alright, so now we can get back to our question of deciding on a standard description of an algorithm, how to do that, how to format it. So now we're starting to talk about that, how to create a standard description for an algorithm. Well, so now it's sort of getting into the specifications of how to do that. And so the process now is we're going to set up a format, the way it's written out on the page, so to speak, a description of an algorithm, how to do that, and a notation that we'll use for this description, for describing Turing machines. Turing machines, algorithms, well, they're pretty much synonymous from now on. Okay, been saying that. I mean, this is taking verbatim, literally from the text, and you notice we've been talking about the context of describing algorithms, and here he's got describing TMs, and I don't know if that's a slip, but it doesn't matter because effectively they're the same, right? Because, as I keep saying, think of an algorithm as a Turing algorithm. It's an algorithm implemented by a Turing machine. So in describing the Turing machine, you're describing the algorithm and vice versa. Pretty well synonymous. Okay? Alright, so the first thing we'll talk about is the input to the Turing machine. The input to the algorithm, in a sense. So for the rest of this session, we'll be talking about the input. Now, for a Turing machine, the input is a string. Okay. So the input to a Turing machine is always a string. Okay. So first thing. Talking about the creation of a standard description of an algorithm, and hence the corresponding Turing machine that implements it. So we'll talk now about standards, formatting and notation and so forth of the string. That's the first item on the agenda, so to speak. Right. So if your Turing machine always has as input the string, then how do you put your problem, so to speak, into the Turing machine? How do you put the technical word is to represent. So how do you represent a problem in the form of a string? And that leads into representation theory. So, for example, the mathematical object that you're talking about might be a graph. What else could it be? It could be a polynomial, might be a grammar, could be an automaton, or any sort of combination. So how do you, as I was saying, the technical word is represent. How do you represent that mathematical object in the form of a string? Because you need to do that. You need to, in a sense, translate what the mathematical object is into the string. And then you can have the Turing machine, just a minute, so you can go around. My wife's just come back from a weekend trip. I found it, okay, terribly distracting. Okay, so you can then have your Turing machine decode the string. So to put the information about the object that you're talking about, the mathematical thing that you're going to manipulate, or the problem concerns. Like it might be a graph problem, it might be a grammar problem, or whatever. Whatever that thing is, the object, as it's called. You need to translate that into string form so that the Turing machine that's implementing the algorithm can input can have as input that that the Turing machine can read and then decode. So it then does the opposite, like to translate, or technical word is encode or represent. You encode the information about your object into the string. That string then goes into the Turing machine, and then the Turing machine does the opposite process. It decodes. In other words, it extracts the information about the object, like whether it's a grammar or a graph or polynomial or whatever it is. So the Turing machine, as part of its program, it then decodes that information. It extracts the information from the string and then starts manipulating that information to solve whatever the problem is. Okay. All right. So now talk a bit about encoding or representation. How do you put information into string form? How do you generate strings that encode the information that you want to go into the Turing machine, so that it can implement your algorithm? Right. So now we'll talk a little bit about notation. So say you have some mathematical object or some object. Just say big O. That's not a 0. That's an O, the letter O. Right. And then you translate it, if you like, or you represent it in the form of a string. Then the notation you use for that transformed or encoded object O is written with O, but angular brackets around it. Okay, so you start with your object O, whatever it is, graph, polynomial, whatever, and you encode that into a string. You've put your information into string form. Maybe your string is a binary string. So you're putting information into a binary string. You're representing information in terms of zeros and ones in a binary string. So that object O, the representation, the encoding, is represented this way. This is the notation, just angular brackets with the O in the middle, right? So if you see this, you'll know it's some kind of encoded information. Now, if you have several objects, graphs, polynomials, whatever, you can say you've got object 1, object 2, ... object k. So if you have k of these objects, well, you just do something similar. You'd have these commas here, and you'd have the angular brackets either side. I don't know if you can see the second line on the next session, but you can still put it into a single string. So you'd have left angular bracket object 1, O1, comma O2, comma ... OK, the kth object, and right angular bracket. Okay, and you can encode. You can do that in many different ways. But the point is, you're translating, encoding your information of the objects you're talking about into string form, so that the string can be input to the Turing machine, because Turing machines accept as input strings.